Hello, my name is Rogier, and I'm going to tell you something about distributed computing at our company, bol.com. But first of all, please notice that the story I'm going to tell you happened in a time when we weren't running in the cloud yet. So back then we were still running our own virtual machines in our own data center, and temporary adding more hardware was kind of a thing. So it's a lot easier nowadays when you have a flexible Kubernetes cluster. But back then, yeah, we hadn't such a mechanism. So please keep that in mind while listening to this presentation. First, let me explain who we are. We started in 1999 with only 26 employees as the first online bookstore of the Netherlands, and we slowly expanded our business with some new categories. And not long after our launch, we introduced the concept of a marketplace. So we were basically a platform where other people could sell their second-hand stuff and new products as well through our website. Now today we have around 20,000 partners who sell their stuff through bol.com. So if you want something to play, if you want to buy a game, or if you want a game console, or maybe even domestic products, we sell them. So long for the history, because I wanted to talk about the assets we are processing. We currently have about 100 million assets in our systems, and each day we receive 12 million new URLs pointing to external images from our suppliers, which we need to process. We have a multi-channel approach, so we are processing image for the apps, for the social, for mobile, desktop, email campaigns, you name it. But we also have a nice third-party RESTful JSON API, which is being used by external companies as well. This is our webshop, and let's focus on a specific asset, this Philips Rogier device. Now let me tell you what exactly happens before this asset, this image, arrives at the webshop. Here you see a simplified schema of our asset flow. It all starts with fetching the original asset from our partner's servers. We save the high-resolution one in a store, and then we match that product against our internal IDs. And after a successful match, we trigger the render process, which pre-renders the original into several web-optimized formats. And each format will be saved to disk, from where it will be served to our customers using good old Nginx. And everything is linked together through an event system. So far, so good. Then, at some day, I read a few articles about web page sizes, about how it really affects the customer journey, and in the end, of course, sales. So the smaller the site, and the bigger the revenue. And during that same period, Google introduced getsee. Besides being difficult to pronounce, I think it's some kind of cookie, getsee, I'm not sure, but it is a new open source JPEG encoder, and it's a simple standalone command line tool, which is available for all platforms. And you can use it to reduce JPEG file size. And the results were great. You will gain an image size reduction between 30 and 45%. So you can shrink images without losing perceived quality in image size. So let's try it. Take this original Philips Rogier, and let's open a terminal and apply the getsee algorithm. See what happens. Now, getsee is being running now, and all kinds of magic happens. Data science models are applied, all doing fancy image stuff, without reducing the perceptual quality. As you can see, it takes quite a long time to apply the algorithm on this one file. Now, this is a screencast, so it's in an endless loop, but you could see that the whole process took about 25 seconds. But yeah, the results are great. File indeed reduced a lot. The original was 87, and after applying getsee, it's 64. So this is quite a big reduction, and I don't see any differences in quality. So let's do it for all our assets. But 25 seconds is quite long, so with our volume of incoming data, this is undoable. So I had an idea. Back to the flow. Please notice here that our renderer of the original to the disk is a synchronous step. So speed is important there, and we can't make it slower by applying the getsee model here. So I thought, let's put a pointer to the rendition on the disk in a queue, so we can apply the getsee algorithm asynchronously after creating the initial rendition. So we created a queue, and on the render nodes, we also started to run 3 worker nodes. All of them had just one specific job, processing messages from that queue and apply the getsee algorithm. Each worker gets the freshly rendered asset from the store, applies the algorithm, and then eventually it replaces the one with the smaller variant. Simple as that, so everybody happy. But then, queues were full. The number of messages in the queue piled up, and I calculated that in order to process retroactively all our assets, it would take literally years. Then at some day, I was doing a running exercise on a dike nearby Nijmegen, so that's where I live. And exactly at this point, an idea popped up in my head. But before I'll tell you that idea, I have to tell you something about our company. We are quite big now. We have about 2,000 colleagues. And if you want to get decent IT professionals nowadays, you need to support the hipster life. People nowadays want a gaming room, and they want to have fancy coffee brewing meetings, and they even want to sit in a bath full of balls. I don't know why, but they also have shiny MacBooks. And MacBooks are fast. And they have fast GPUs, and they have a lot of idle time. Because while sipping on their latte macchiato, all these MacBooks are doing absolutely nothing. It's kind of a waste, right? So, back to our flow. I thought, let's add 2 new endpoints. The first one, get work, gives the possibility to get a fresh rendition from the render store, where the getsee algorithm is not yet being applied to. And the second one, a post endpoint, where you can give back a rendition after the getsee algorithm has been applied. Now, basically, these 2 endpoints give us the ability to distribute the getsee work over our colleagues' laptops. So the next thing was to create a small command line tool, which can run on their laptop. And here you go, our own distributed horizontal scaling getsee queue processor. Everything running on the laptops of our colleagues, and it really scales. So let me explain how I created this client. This is where Go comes in handy, because not all colleagues have MacBooks. We also have Linux and Windows machines. And Go cross-compiling really make it easy to produce binaries for these platforms. Also, due to the fact that the outcome of the compiler is just a single binary, it makes it very easy to install this on their laptops. I needed to make the getsee binary also available on their laptops, so I used a package called Go bin data. I'm sure you all are familiar with that, which allows me to embed getsee into our own binary. And after starting, I simply saved the file to the user's home directory, made it executable, and there you go. Of course, I also wanted to be in control of the client's versions, so I built in an update mechanism, and last but not least, we created a thing where people could opt in, because I didn't want to force everybody to participate. So, how does it work? When a colleague was opted in, the binary was pushed to their laptop and automatically started. And while running, the following happens. First, the client does a GET request for work. Its version number is sent along as a header, and if the renderer service thinks that his version is outdated, then the update mechanism kicks in. And the next step is that the renderer checks the queue. If there is a message on that queue, then it fetches the synchronously created rendition from disk. It creates a base 64 string representation of that rendition, and it sends it along with some other information to the colleague's laptop, where the getsee binary is being applied. And as you saw, this takes a while, but when it's done, then it delivers the work, so the smaller file size. It delivers it back to the renderer, which completes the transaction by replacing the bigger file with a smaller file. Easy, right? So to make it even more fun, we added some gamification. We kept track of who applied the most image reductions, and we arranged some prizes for the top 3 workers. We created a dashboard with some metrics, and it didn't took us that long before 500 colleagues ran their client every day, making the webshop basically better. People had fun of it, and we even started to receive pull requests. People were improving dashboards. People created Ansible scripts to get on top of the stats. Some even wrapped the binary in as a screensaver, so it was a fun thing. And it didn't took us that long to empty the queue. So from this stupid pet project, this brought us something, way smaller images on the webshop. So what can I conclude? Like I started the presentation, if you have a Kubernetes cluster, then you can easily horizontal scale pods, and then you have no problem at all. But back then we didn't have such a mechanism. So yeah, of course, I don't recommend using your colleague's laptop to run business stuff on it. But it was just a fun project, which turns out to bring great results. So what to conclude then? Well, maybe start running every now and then. It gives you fun ideas, and it's good for your health as well. Thanks. If you have questions. Sorry? Did you?
So after this project and the success of it, have you guys tried to do other stuff with the same approach?
No, nowadays we are running in Kubernetes, and we use cloud functions in Google to do the render process, which scale perfectly. So it was used for the initial apply of that getsee model, and yeah, back then it wasn't that simple to scale up. So no, we don't use it anymore on production now. No.
Did you control somehow that the client is only running in idle times, or did it just run all the time?
No control whatsoever. So they could shut it down themselves if their fan was spinning too loud, because it was. We only had one requirement from the security department, because we want to prevent people sending back dick pics or whatever, because people do that kind of stuff. So I had to implement a p-hash mechanism to compare both images.